In the last segment, we took a look at the solution to the 2D heat diffusion equation in the case of a square plate. And in one case, we had an unrealistic boundary condition and it resulted in a nice solution. In the other one, we had a more realistic boundary condition. And the solution that came out of that was an infinite series. And so what we find is if we look at a lot of different solutions to the heat diffusion equation, there really are not that many for complex geometries that we would find in real-world applications. And so given that, the net result is that if we're studying complex shapes, numerical solutions are typically used to determine the temperature distribution in three dimensions within an object. And you can also do time as well. It could be a transient solution. But that is typically what is done if you have a complex shape. Now, there are some cases where there's kind of an in-between area that we can use things in. And this is referred to as being shape factors. Shape factors still do have use in certain things. If you're looking at pipe flow and you don't want to do, as an example, pipe flow and you don't want to do full complex numerical solutions along the pipe to model the heat transfer, you could use something like a shape factor. And that's what we're going to look at in this segment. So shape factors have been tabulated for a number of two-dimensional shapes that are too complex to use the heat diffusion equation to solve. And the nice thing about a shape factor is it gives us kind of a quick and dirty way of being able to calculate heat transfer from one object to another. So let's take a look at shape factors now. So what the shape factor is, it's a technique or a method that enables us to compute heat transfer between a certain geometry and its surroundings. And the way that we do this is we have an equation, Q equals Ks delta T. So in a way, it's kind of like a Fourier's law, but delta T is overall. And what we have in here, K will be the thermal conductivity of the material that we're looking at. S is the shape factor. And so S itself is the shape factor. And K is the thermal conductivity of the material that we're looking at, and delta T overall is the temperature difference between the two systems that we're transferring the heat between. And it'll make more sense when we look at an example problem. I said that this looks like Fourier's law, but in the looking at it closer, it does have thermal conductivity, but also kind of looks like Newton's law of cooling. So it's a bit of a mix between the two. But anyways, that is the shape factor. And so values of the shape factor are tabulated. You can find them in books. And for different shapes. I should call it objects because they are shape factors we're talking about, but for different objects, for example. So it might be a sphere buried below a surface and it's not very far below the surface. So here, obviously, we would not have only radial conduction going on. We have the presence of this surface, and that is going to cause this to become a two-dimensional problem versus just a one-dimensional problem. So that could be an example of what you'd find with the shape factor. But what we'll do next in the next segment is we're going to take a look at solving a problem using the shape factor. But look in any textbook and you'll find many, many different shape factors.